Okay, should be recording. Okay, so polynomial functions, let's start by reviewing the things that the types of functions that we've already studied. Okay, so what we know so far. Okay, so the first thing we know are these things called linear functions. When we first talked about linear functions, we actually looked at them as equations that look like this: y equals mx plus b. You remember that the m was the slope and the b was the y-intercept, and basically this was a line. Well, if we replace the y with f of x, then we have a function. It's the same thing, but it's different notation. So that is a linear function. We know that when we graph these, they'll look like a line. And most of the time they have an x-intercept and they have a y-intercept. Depending on if the line's vertical, it may not have a y-intercept. If it's horizontal, it may not have an x-intercept. But in general, most lines have an x and a y-intercept. So we have an x-intercept and we have a y-intercept, and we learned how to find those when we were talking about graphing lines. Okay, after we talked about linear functions, the next thing we talked about, and this was what was on the last test, are quadratic functions. Now, with quadratic functions, they don't look like lines, right? They look like these things called parabolas. But the equation for a quadratic function looks like this. And if we replace the y with f of x, we just have different notation, but it draws the same picture. And we learned how there's a set of steps on how to go about graphing these. You have to figure out if it opens up or down. You have to find the vertex, do a quick sketch, see if you have any x-intercepts, find them if you do, and then find the y-intercept and then draw your parabola, and then you're done. So we know that these look like little U's, and it could open up or down, but generally speaking, we always have a y-intercept, and sometimes we have x-intercepts, sometimes we don't, sometimes we have one, sometimes we have two, but we don't have more than two, right? Two is the most number of x-intercepts you can have here. So what I want you to pay attention to right now is the variable in both of these functions we've looked at. Once you look at the variable x, you'll notice that in the linear function, the highest power of x that we had was 1. And in the quadratic, the highest power we have is 2, right? And so to be a linear function, you need to have x raised to the first power. To be a quadratic function, you need to have an x raised to the second power. So that leads us into what are polynomial functions. Well, polynomial functions are functions that have x raised to powers that could be 1, 2, 3. Basically, there's no limit to how big that power gets. So what I'd like to do is below each of these examples, or below each of these things, I want to give you a specific example. So an example of a linear function would be like 2x minus 3. That's an example of a linear function. F of x equals, I'm going to write this two different ways. For a quadratic, we could have something like x minus 4 times x plus 1. So that's a quadratic function that I've already factored. I'm going to actually multiply it out. I'm going to FOIL it out. I'm just going to kind of do that in my head. So what you should be paying attention to is for the quadratic function, if we're given that function in the blue, we should be able to factor it to get it back to this other version here in the green. And that's what we did when we wanted to find the x-intercepts. So I just wanted to give you two examples, and now I'd like to actually graph both of those. So 2x minus 3, let me get rid of that. So I'm going to write 2x minus 3. So this is some graphing software called, or not software, it's a website called Desmos. you can always go here and graph things. So I'm going to graph 2x minus 3, and then the other one was x minus 4 plus 1. Okay, so let me now show those. There's the 2x minus 3, our nice line. And then here is our parabola. Okay, so if we're going to be talking about polynomial functions, the word poly stands for many. Okay, so we have many monomials, and a monomial is a single term. So let me just give you an example of a polynomial. Okay, let me give you an example of a polynomial. And then we'll talk about, there's a general formula for it, but I want us to look at examples first. So what if I take, let's take this quadratic up here. Let's take that, x minus 4 times x plus 1. So that would be a quadratic function. But what I want to do now is I want to multiply it by another x. So I'm just going to multiply by, let's say, x squared. Okay? Now, if I did that and multiplied that all out, I'm not going to go through the steps. I just want you to see what it would become. It would become x to the 4th minus 3x to the 3rd minus 4x squared. So this, in yellow, is what we refer to as a polynomial function. It has x in it. Now, what is the highest power of x that we see here? So what's the highest power that you see?
4.
4, okay. So 4 here, okay, 4, the highest power of x, that is known as the degree of the polynomial. Okay, it's called the degree of the polynomial. So that example that I just gave you is what we would refer to as a 4th degree polynomial. Now, let's go take a look at it and let's see, you know, what its characteristics are. Like, what does the graph look like? So what I'm going to do is I'm going to take this one. I think I can duplicate this. Wait a minute, I did this earlier. Oh, it's right here. Duplicate that. And now all I'm going to do is add the x squared to the back. Okay, so I'm going to take the line out so we don't get distracted by it. So I'm also going to change the color. We should be able to change color. Okay, so the red one here is this 4th degree polynomial, and then the green one is the quadratic. So I'm going to zoom out here. Okay, and now I think I'll take the quadratic out of here so you can really see this 4th degree polynomial. So notice that it kind of looks like a parabola in the sense that the left side and the right side seem to go up, but it's not like a perfect U. At the bottom here, it's doing some weird stuff. It's like curving back and then goes down and back up. So it's not a parabola, it's something else, right? But it still looks like the left and right hand sides go up. Let's see, what would happen if instead of doing that x squared at the end, what if I just did x? So what I'm saying is, what if I did that instead of that x squared I tacked on, let's do a different function, a different example where I take that original parabola and I just tack an x here instead. So if I multiply that together, again, I'm not going to go through the steps of that. Here's what I get. So what would the degree of that polynomial be? What's the highest power of x?
3.
3, right? So we have a 3rd degree polynomial, all right? So let's go take a look and see what it looks like. So I'm going to take this and I'm going to change that to just x. And let me see if I can change the color again. Let's make this one purple. Done. Okay, so do you see the purple one? It doesn't look a whole lot like the red one. Things have changed. It looks like the left side, this left side, looks like it just goes down and down and down, right? And the right side seems like it's going up. Now, there's something happening. Let me zoom in here. Do you all see something that all of these have in common? The parabola, so the green one, the red one, and the purple one, they all have something in common. Can you all see what it is?
-1 and 4.
-1 and 4. Those are x-intercepts, aren't they?
Yes.
And so all of these have the same x-intercepts. At least they share two. So on the green one, you can see on the green one here, we have an x-intercept right there. And then on the green one, we also have an x-intercept here, but so do the purple and the red. And the reason why is because they all have the same factors, x minus 4, x plus 1. Since they all have those factors, if we were to set those equal to 0, we would get 4 and -1. Those would be our two answers. So they share something. They have that in common. Otherwise, there's a bunch of other weird things happening. Now, let me kind of really throw a wrench in this. What I'm going to do is I'm going to take this parabola, I'm going to copy it. Here we go. And what I'm going to do is I'm not going to add an x to the outside. I'm actually going to square the x plus 1. So if I do that, it's going to run out of colors here, orange. So do you see that the green and the orange, they still have the same x-intercepts? They have -1 and 4. But the orange one is very different in its shape too. So all I'm trying to get you to see here right now is that a polynomial is just an expression that has x raised to powers that are bigger than 2, because we already dealt with x to the first power, x squared. We want to be able to look at x to the third, x to the fourth, so degrees that are higher than 2. And we can see that the graphs are very different. You know, I mean, if I put all of these on here now, you can see all those graphs are very different. But our goal is to be able to graph them. And so that's going to be somewhat problematic. But when I'm done showing you, I think you'll agree with me that it's not as bad as you would think it would be. Like, you would think that that would just be so difficult to graph one of those. So why don't we get started? I'm gonna give us an example, and I'm gonna try and get us to sketch it, all right? And then as I do a few examples, hopefully you'll catch on and you'll be like, yeah, that's not so bad. Okay, so first example here that we want to actually sketch. Let's try and sketch this polynomial. F of x equals x plus 1 times x minus 3 times x plus 6. Okay, so notice that I've given you this function already factored. Is that clear to everybody? That this function is factored because it's broken up as something times something times something. So you have to make sure you understand that right now it is factored. Any questions on that? Okay, now, when we look at a polynomial, if it is factored already for us, we can find the x-intercepts really easily. Does anyone have an idea of how we can find the x-intercepts? How did we find the x-intercepts for a quadratic? Wouldn't we factor? I know we use a quadratic formula, but wasn't one of the techniques to factor it and then to set each factor equal to 0? Well, we can do the exact same thing here. All we have to do is take each factor, set it equal to 0. So we're actually going to be doing 3 equations. Okay, so I'm setting each factor equal to 0. Here I just subtract 1, we get x is -1. Here we add 3, we get x is 3. Here we subtract 6, we get x is -6. Do you all follow that? Any questions there? Okay, so here's what I know so far. If I were to graph this, if I were to go to graph it, I know that at -6, my graph touches here. I've got, not touches, I have a dot right there. At -1, I have a dot. And I know that at 3, I have a dot. But that's all I know so far. Would you all agree? That's all we know.
Yeah.
Yeah, so the next part is how do we determine the rest of it, right? So I'm going to go to the graphing software here. I'm going to get rid of all this stuff. I'm going to have this graph it for us. It was x, sorry, hold on, plus, I forgot, 4? Was it 4? Oh, x plus 1 minus 3. X plus 1, x minus 3, x plus 6. Okay, so there's the graph. It's crazy looking. Looks like it goes up and then back down and then back up. And sure enough, if you look at this, we have the x-intercepts where we thought we would, right? At -6, -1, and 3. But how in the world do we determine the rest of this, right? That seems difficult. Well, there's a shortcut way to do it, all right? And I'm going to show that. I'm going to share that with you right now. So what we need to do now is we need to determine what's called the end behavior. And what I mean by that is, you know, like on a parabola, the parabola, when we said it opened up, you could say that both ends go up, right? And if a parabola opens down, you could say that both ends go down. There is a short way to determine for a polynomial what happens at the ends. And with polynomials, it's a little different than quadratics. With polynomials, you either have both ends go up, both ends go down, or it's like a mixture. It's one side goes up, the other goes down, or the other way around. So there's a couple of steps to do it, but it's not that bad once you figure it out, okay, or once you know what it is. So here's how we determine the end behavior. The first thing you have to do is find the degree of the polynomial. You have to know the degree, all right? Find degree of, I'm just gonna put poly. Now think about that. The degree is the highest power of x. So it's either gonna be 1, 2, 3, 4, 5, 6. It's gonna be some number, some counting number. So we should be able to find that degree with relative ease. Once we find the degree, the next thing we do is we find what's called the leading coefficient. And the leading coefficient, all that is the number in front of highest power of x. Okay, so the leading coefficient is the number, not the x. It's the number that's in front of that highest power of x. Once you find these two things, you can determine what happens on the end of the polynomial. So here's how you do it. I'm going to make a table because a table makes this easier to understand most of the time. Okay, so in this table, the way this works is I'm going to put here, let's go leading, I'm going to put LC for leading coefficient. So leading coefficient from now I'm going to abbreviate LC. Leading coefficient positive, leading coefficient negative. And then on this side, I'm going to put degree even, or degree odd. Okay, so let me explain. When you find the degree, right? When you find the degree, we said that that number is either going to be 1, 2, 3, 4, 5, 6, 7, 8, whatever it is. What you're going to be looking at is whether or not that degree is even or odd, okay? And then you're going to look at the leading coefficient and you're going to be asking yourself, is it positive or negative? So let's say that we have a polynomial given to us that has an even degree, okay? So an even degree and a positive leading coefficient. Well, that means in this table, I'm looking in this first box, and let me tell you what happens. If we have that situation, then you're guaranteed that the left side of the polynomial goes up and the right side goes up. And in the middle, I'm gonna put a question mark. It could be doing all sorts of squiggly, wavy things, but I can tell you that the ends have to go up forever. Now, if let's say we have an even degree, but a negative leading coefficient, well, that's going to be different. What's going to happen is the left side's going to go down, the right side's going to go down, and in the middle, it may squiggle around, but I know that both sides go down. Does that make sense, how this table's working? Any questions on it? Now, what if we have an odd degree and a positive leading coefficient? Well, in that case, the left side goes down, the right side goes up, and in the middle, again, it could squiggle around, but eventually it has to go up on the right and down on the left. And then lastly, if we have, not the colors here, but if we have an odd degree and a negative leading coefficient, then it's the opposite of the first one. The left side goes up and the right side goes down. So this table right here, I will provide you on a test. You don't have to memorize that, okay? So all polynomials, all of them, every single polynomial out there, when you graph it, it's going to be one of these four things happening. Either both sides go up, both sides go down, one side goes up, or the other way around, okay? So it's kind of like this weird dance, I guess. All right, so for the problem that we were just looking at, let's see if we can do this. And by the way, I should tell you that this whole thing that we're doing here is called the leading coefficient test. The leading coefficient test. It's a test that we run to see what's happening to determine the end behavior of the polynomial. Okay, so back up here. We already know where this thing hit the x-axis. We know that, but we didn't know anything else. So looking at this right here, and this is where things get a little tricky. Looking at this right here, can somebody take a guess as to what the degree of this polynomial is and maybe explain why you're coming up with that? Anyone have an idea of what the degree of this would be? Take a guess.
3.
If you were to multiply all those things together, what do you think the highest power of x you would have would be? I thought I heard someone say something, but it didn't come through.
So you said the highest power of x?
Yeah.
3.
3. Okay, so why do you think 3?
Because there's 3 x's in that problem right.
Yeah, so if we multiplied it together, think about it this way. If we multiply just the first 2 together, wouldn't that be a quadratic? Because you'd FOIL it out and you get a quadratic. Multiply by this third factor, quadratic, which should make it a third degree. Do y'all follow that?
Yeah.
This should be a third degree. Okay, a third degree polynomial. Now, the leading coefficient's a little harder. The leading coefficient, the way you get the leading coefficient is by looking at all the numbers that are in front of these x's. So you see we have a 1 in front of the first x, a 1 in front of the second x, and a 1 in front of the third x. Those are all going to have to multiply times each other at some point. And so if you multiply 1 times 1 times 1, you should just get 1. So our leading coefficient should be 1. Try and squeeze something in here. So what I'm getting at is this. This first guy right here really, at the end of the day, looks like a 1x. The +1 does contribute, but if we're just looking at the x's, that looks like a 1x. This one looks like a 1x, and this one kind of looks like a 1x. And if we multiply those all together, we wind up getting a 1x cubed. And so the degree, right, the degree is the 3, and then the leading coefficient is the 1. Okay? Any questions there? Okay, so we have this is a degree 3 polynomial with a leading coefficient of 1. So when we make the box, let's say A, B, C, or D. Which case would it be? Would we be A, B, C, or D? Three? Degree, yeah, it would be C, because the degree is odd, right? Because the degree was 3, so that's an odd number. And then the leading coefficient was, so okay, we're looking at degree, leading coefficient, we have to be there. Does that make sense, everyone?
Can you repeat that one more time? You were cutting out.
Okay, yeah, so the degree was 3, which is odd. So that means we're on the bottom row here. We're looking at the bottom. On the left column. So we have to be on the bottom row in the left column. So bottom row, but the left column, which means you have to be C. Does that make sense? Are we good?
Your volume
Kind of.
is a lot.
You actually cut it out when cut out again when you explained
Really?
it.
Okay, I'm going to take my video off because sometimes that helps. You know what? Yeah, I'll just take my video off. That'll Can you all hear me?
Yes.
Okay. I'm not sure what in the world happened here. Okay, so we're good or no?
Yeah, right now it's not cutting out.
Okay, and you can see my screen still?
No.
No?
You just see your picture. I just see your picture.
Okay, let me try and share the screen again. How's that?
Yeah, now I can see it.
Okay. Okay, so we're gonna try and continue here. Sorry about that. Okay, so I was right now should look like C. Were there any questions on that?
Can you explain it one more time? I'm sorry, it cut out both times.
Yeah, no problem. So our degree of our polynomial up here is 3, which is an odd number, which means that we are looking, it's either going to be C or D because it's odd. Okay. But our leading coefficient is 1, which means that it's got to be down, it's got to be in the first column here because 1 is positive. So if you've got to be in the bottom row, but the first column, then that must be C. Does that make sense?
Yeah, so positive is always going to be B and odd's always going to be C.
Positives what?
Always going to be A, and then odds are always going to be C.
If your leading coefficient is positive, you're either going to be A or C. But if your degree is odd, then you have to be either C or D. So you have to look at both things at the same time. Like if you just look at the leading coefficient, it narrows it down to 2 possibilities. But then the degree narrows it down to 2 possibilities, but then it can only, it's where they overlap, I guess, what they both have in common. Let us do another one after this, and then hopefully you'll pick up on it. Does that sound fair?
Yes.
Okay. Okay, so now let me go and put this together. So what we know from this graph, okay, I know I'm just going to jot it down the side here. I know that my left side goes down and my right side goes up. And in the middle, I don't know what it looks like. Okay, that's what we've determined from the leading coefficient test. So now what I'd like to do, I'm going to bring my video back up here and see if it holds up. So now what I'd like to do is put this together. I know that my graph must go down on the left and up on the right. So I'm going to just kind of go to my graph right now, and I just want you to watch what I do here. Over here, far to the left, I'm just going to put an arrow that goes down. Then to the right, I'm going to put an arrow that goes up like that. Do y'all see that? Okay, now the next part is to determine what happens in between, in the middle. And we know we have to hit those 3 points, right? So does this make sense that it could do this? Does that make sense that it could look like that?
Yes.
Okay. But couldn't it also have done this? Like what's in red there would have still done the same thing. Left side went down, right side went up. But in the middle, there's some other different things happening than the blue. So even at this point, we still don't have enough. And don't worry, if you're lost, I'm going to summarize all this. I just wanted to work through an example. So here's what it really looks like, right? Remember, this is what it really looks like. And here's where we are, and we're trying to figure out what's going on. And all we know for sure is that those 3 points are there and that the left side goes down, right side goes up. So the last part of this, to figure out what's going on in the middle, is to I'm gonna run out of room here, so I'm gonna have to go, you know what, I'm gonna do it up here. I'm gonna erase some of the stuff I have up here. So the next thing I need to do, this will be the last step, is I need to determine what's called the multiplicity. Of each X-intercept. Okay, so how many X-intercepts do I have?
3.
3. Okay, so for each one, I have to determine this thing called the multiplicity. And the way you do it, it's very simple, but you have to be careful with it, okay? All you do is you look at, okay, let's look at our first X-intercept, -1, right? Where did that come from? That came from this X plus 1, right? And we set it equal to 0. What I want you to do is look at that X plus 1 and ask yourself, what is the power outside this parentheses? So what is that power that's right there outside the parentheses? So it's like, it's X plus 1 raised to what power? Do you know? If there's nothing there, then what is it really? A 1, right? It's a 1. So there's a 1 on this parenthesis, and there's also 1 on the next parenthesis and a 1 on the next. Okay, those numbers are what you use to determine the multiplicity. All right. If it's an odd number, you will cross through the x-axis. That means when you draw it, you're going to take your pen, you're going to cross through the x-axis. If it's an even multiplicity, then you're going to bounce off the x-axis. Now you'll have to see this in an example, okay? And I'll do another example in a second. So would you all agree that for every x-intercept we have here, the multiplicity for each one is odd, right? Because each one of them has a 1 up there outside the parenthesis. So they all have odd multiplicities, which means we should cross through when we draw through those points. So going back to my picture, remember I had my blue graph down here. I know the bottom left went down. Now, when I get to -6, when I start drawing, when I get to -6, what should I do?
Cross it.
Cross it. So I'm going to just cross through the x-axis, okay, instead of bouncing off. And then I have to, this is almost like back in kindergarten, first grade, I'm trying to connect the dots, but I can't just do it however I want. I have to follow the rules here. So when I get to -1, I have to turn back, I have to go to -1, and when I get there, I have to cross through the x-axis again. But I have to get back to 3, so when I get to 3, I have to cross through again because the multiplicity was odd. And then I connect it to that right side going up. And that is my picture. Wow, that's a lot, right? It's a lot to have to absorb. You know, let me make sure I am recording. Okay, I'm recording, it's still recording, okay. So here's what we're gonna do. I'm gonna start over. I'm gonna give you the set of steps first, and then we're gonna run through a new example. Steps to sketch polynomial function. First step, make sure it's a polynomial. Okay, second step, use leading coefficient test to determine end behavior. Okay, third step, find the X-intercepts and the multiplicities. Of each one. Fourth step, plot the X-intercepts. And the end behavior. And then connect the dots. Okay, that's it. Those are the steps. So let's take the example that we just did, okay? Excellent. We're just going to run through all the steps on this one, even though we've already done it. Okay, step one. Is it a polynomial? Yes, it's a polynomial. Step two, use a leading coefficient test. So we'd have to find the degree. The degree we already said was 3. The leading coefficient we said was 1. The degree is odd and the leading coefficient is positive. And from the table, which I don't want to draw the whole table again, but what we know is that it was this one, option C, right? So we know that the left side goes down, the right side goes up. And in the middle, we aren't sure. Step 3 was to find the X-intercepts, which we set each of the factors equal to 0, and we got -1, 3, and -6. And then we determine the multiplicities at each one. So the multiplicity at each one was an odd number. So that meant that we were going to cross here, and cross here. I know I'm going through this fast, but we just went through that example. So I'm leaving out a lot of the detail here. The fourth step is to plot everything. So what we would do is we'd start out, we would plot our X-intercepts. We would put our end behavior. And then we would connect the dots, making sure to pay attention to the crossing. So we cross through, come down, cross through, and connect. All right? And that's it. Everybody's graph is going to look a little bit different. Like somebody else might have done it and it may look like this. So what's in red would still be correct and you would get full credit for that. How high these little arcs go, how high up they go, doesn't matter. How low they go, doesn't matter. If you wanted to know how high they went and how low they went, you would take a calculus class. In there, we can determine these peaks and valleys, like what they are. But here, all we care about is the X-intercepts, the end behavior, and really whether or not your graph is above or below the X-axis, in between the X-intercepts. So that's it. Those are the steps. That's the procedure. I think we should do another one. Any questions? How about this? Wait, hold on. I'm doing this wrong. Okay, is that the same problem we just did?
No.
It is not.
No.
It's not, and the big difference is that squared there. And that makes a huge difference in what this thing looks like, all right? So let's go through the process. First thing, is this a polynomial function? Yes, it's a polynomial function. Second, we need to determine the left and right-hand behavior. That means we need to know the degree. Now the degree is a little bit tricky, everyone. Okay. So what is this first one? What is it really acting like? Like if the 1 wasn't there, what would it really be? I mean, what would it be if that 1 wasn't there? It'd really just be like a 1x, wouldn't it? 1
Yeah.
times x, because there's a 1 in front. Okay. Now this one right here, be careful. What would that be? If that 3 wasn't there, that would really be like a 1x, right? But what about squaring it? What would that do to it?
X squared.
Yeah, it would just look like a 1x squared. And then what about this last one? If the 6 wasn't there, that would again look like a 1x. Now, if you multiply those 3 together, this will give you your degree and your leading coefficient. So that multiplied together, you get 1, and then x to what power?
3. The
X.
third part.
Oh, we have x
Four.
times x squared times x, so x to the 4th, right? Do y'all see that?
Yes.
So what is the degree of this polynomial?
4.
4, okay, and 4 is an even number. So we're looking at, when we look at degree, we're looking at odd or even. And then what is the leading coefficient of this thing? Leading coefficient. What is the leading coefficient of this polynomial? Well, that just comes from that number right there, right? The 1 in front of the x to the 4th. So that should be 1. And when it comes to leading coefficients, we just need to know if it's positive or negative. And here it's positive. So let me go back to that table and let's talk about what case we have here. We have an even degree and a positive leading coefficient. An even degree and a positive leading coefficient. So what case would we have here? If we have an even degree and a positive leading coefficient, A, B, or C?
A.
A. Okay, so even degree means it has to be one of these two, but a positive leading coefficient means it has to be one of these two. And the only one that they have in common is the A. So that tells us that both sides go up. Okay, so what we know is that when we graph this, the left side goes up, the right side goes up, in the middle, we don't know. That's step 2. Step 3 is to find the x-intercepts. So all we do for that is set each of the factors equal to 0. Now, I'm going to do these over here. Now, let me point something out. In yellow here, I have x minus 3 squared. Oops, no, I don't. I just erased it on accident. We have x minus 3 squared, right? That just means x minus 3 twice, right? That just means x minus 3 times x minus 3. So if I set that equal to 0, I only have to set one of them equal to 0. I just set x minus 3 equal to 0, and then I don't need to do that 2 times because I'm going to get the same answer both times. Would y'all agree with that? So how many x-intercepts do we have, and what are they? So what are my x-intercepts here? So from here, it's what?
-1.
-1, and then from here, we get x is 3, right? And then from here, if we solve, we get x is -6. Aren't those the same x-intercepts that we had from the previous example? Same thing. Now, the end behavior is different, right? Both sides go up. In the previous example, left side went down, right side went up. But here, they both go up. And now there's another difference. Can you tell me with the multiplicity, can you tell me on that first x-intercept, X is -1. Can you tell me whether or not we're going to cross or bounce here? So what's the power on that factor? We go back up, we take a look at this factor. What's the power here? It's 1, right? 1 is an odd number. Since it's odd, we will cross. Okay, on the 3, where did that come from? It came from this factor. Now, what's the power here? It's a 2, right? And 2 is an even number. And what happens when you have an even multiplicity? We don't cross, we do what?
Bounce.
We bounce. So we're going to bounce here. And then finally, we have this one, which came from here, and that has a multiplicity. The power there is 1, so it has an odd multiplicity. Odd multiplicities mean you cross. Just be really careful, because the thing that people mess up is that when they're determining the multiplicity, you know, the odd is crossed, the even is bounce. Sometimes they don't look at that number up here. They're not looking at these numbers. Instead, they're like looking at these numbers. I'm doing them in purple. And those aren't the numbers that tell you multiplicity. The 1, the 3, the 6, that has nothing to do with the crossing and bouncing. It's always the power on the factor that determines the cross and bounce. So just don't make that mistake. Okay, have we done the steps? Let me see. Made sure it was polynomial. We got the end behavior. We found the x-intercepts and the multiplicities. And now we just need to plot. We're going to put the x-intercepts. We're going to write the end behavior, and then we're going to connect the dots like we're in first grade again. Okay, so here comes my picture. Okay, my x-intercepts, -6, put a dot. -1, put a dot. 3, put a dot. My left side goes up. My right side goes up. And now I need to connect them. So here I go. I'm going to start drawing from the left. So I come down. When I get to -6, what am I going to do at -6? Cross or bounce? Cross through, right? So there I go. I crossed. Now, I've got to get and make a turn and go back up to -1. When I get to -1, what am I going to do?
Go back down.
What am I supposed to do?
Oh, I mean, bounce.
At -1, I'm going to cross, right? So I'm going to actually cross through the x-axis. And now I've got to turn back to connect the dot. I'm turning back. And now when I get to 3, what do I do at 3? I bounce. And so I'm going to actually bounce off like a ball off the x-axis and come back up. I'm going to try and connect those best I can. And that is the picture.
I'm sorry, how did you get the bounce again? How did you know it was going to bounce? I see it at the x = 3.
Okay, so what I did is I went back up to where 3 came from. 3 came from this factor right here in blue. And all you do to figure out whether or not you bounce across is to look at that 2, that power right there, right? That power, that 2 is an even number. And if it's even, so if it's a 2 or a 4 or a 6, you're going to bounce there. If it's an odd number, like these were odd, right? 1 and 1, those are odd numbers. If it's odd, you will cross. Does that answer your question?
Yes, it does.
Now let's actually take a look at this if we ask the computer to graph this. So I'm going to duplicate this. So what's in red here was the original one that we did prior to this. The only thing we did in the second one is we changed this to a squared, right? Let's put that one in blue. Yeah, well, all you can do is tell they're different. So I'm going to hide the red one. There's the blue one. Wow, it's really hard to see that. Hold on. Let's do it this way. There we go. So I changed a little bit. That's the graph from the computer. Is that what ours looks like? Do we have the basic characteristics in place? Does it go up on the left forever? They both do, right? Does it cross through at -6? Yes. Does it then drop down below the x-axis and come back to -1? Yes. Now, ours doesn't go down as low as theirs, but again, this isn't a calculus class. We're not trying to find how low it goes. Does it get to -1 and go up? Sure. Does it go back down and bounce off at 3? Yep. And keep going up on the right? Yes. So our graph matches the computer's graph, at least from the perspective of the things that we want to be able to do in this class. It's good enough. The more detail you want, the higher math you have to take. What do y'all think? Exactly. That's what I was thinking too. Shall we do another?
Yeah, sure.
Yeah. Okay. So here, let's try this. All right. So first thing, is this a polynomial? Yes, because if you multiplied that all out, you would just get like x's to different powers. We don't have any like square roots or fractions or anything like that. So this is a polynomial. The next thing is to determine the end behavior. All right, so let's talk about these. Look at this first factor here. That is really acting like x squared, 1x squared. Why? Because it is 1x squared, right? There's nothing next to the x. What is this second factor acting like? So if you ignored that 1 in there, that -1, it would really be a lot like a 1x squared again, right?
1x.
Yeah, and the squared, you have to be careful because that squared there would mean that it would be the 1x, but then squared, right?
Yeah. Yeah, I didn't see this.
But you see it now, you're okay with that?
Yeah. I just didn't see when I wrote it down.
Okay.
So I get it now.
Okay, and then what about this last one? What is this last one acting like?
1x.
1x, okay. So if we were to multiply those together, we get 1 times 1 times 1, that's 1. And then x to what power?
5.
X to the 5th, yeah. Okay, so then what's the degree of this polynomial?
5.
5.
5, okay. And what are we concerned about when it comes to degree? Are we concerned about even, odd, or positive, negative?
Even, odd.
Even, odd. And this is an odd number, right? Okay, what's the leading coefficient?
1.
1, okay. And for leading coefficient, we're concerned about even, odd, or positive, negative?
Positive, negative.
Okay, and it's positive, right?
Yeah.
Okay, so from our table, we have what? It was in what degree? It was odd, right?
So it's going to be C.
It's got to be
And-
C. It's got to be C. Odd degree, positive leading coefficient has to be C. So that means our left side goes down, our right side goes up. So from here, I can tell you that the left side goes down. I'm not quite sure what's happening in the middle yet, and the right side goes up. Okay, third step, X-intercepts. Now the good news is that all we have to do is take each factor, set them equal to 0. So look at that first factor, x squared, right? That means x times x. So it's two of the same thing, x and x. So all I have to do is set one of those equal to 0. X equals 0. The next one is x minus 1 squared. That means x minus 1 twice. So I only have to do that one once. And then the last one is x plus 5 just by itself. And I set that to 0. So now you just solve each of these. The first one is already, it just gives you the answer, x must be 0. The next one is x must be 1, just adding 1 to both sides. And the last one is negative 5, just subtracting 5 from both sides. So those are my x-intercepts. What should I do now?
So we go from like the cross bounce.
Yeah, we have to determine the cross bounce. So that means multiplicity. So that means I'm going to go back up here and I'm going to focus my attention on these powers up here. I have a 2, I have a 2, and here I have a 1, even though it's not there, right? So remember, x squared, that gave us the 0. So what can you tell me is happening at 0? You know what, y'all, hold on real quick. Y'all think about it. Okay, sorry about that. I had a daughter's getting COVID testing today, not because she has any symptoms, but she's having a medical procedure and they want to make sure that she's COVID free before they have the procedure. So I had to figure out where it's going to be. Okay, so you've had some time think about this. At 0, the multiplicity came from x squared. Squared is 2, 2 is even. What does that mean is happening here?
That's a bounce.
It's a bounce. Okay, what's happening at the x-intercept of 1? That came from here, right?
So it's a bounce.
Bounce again. Yep. And then what about this last one?
Cross.
Cross. Does anybody have any questions on how we got bounce, bounce, cross? Because at this point we're ready to draw. Just make sure you put your, wait, say again?
I'm sorry, it's a cross because it's a negative, or?
No, it's because the power on the factor up here in green, the power up there is an odd number.
Okay.
If the power up there is even, you bounce. If the power up there is odd, you cross. It has nothing to do with the number -5. It has to do with the power on that parentheses. Okay, here comes my graph. I'm going to put at x equals 0, I'm going to put a dot. At x equals 1, I'm going to put a dot. And at x equals -5, I'm going to put a dot. And notice I'm not being like real critical about my spacing. I'm just putting them here, making sure they're in the right order. What should I put next? I put the x-intercepts. What else should I put?
Your ends.
Your ends. Make sure you put your ends in right now, okay? So on the left end, I'm supposed to go down. So I'm going to put an arrow over here like this. On the right end, I'm going to go up like that. And now you get to connect the dots, right? I always like to start on the left-hand side. I'm actually going to do it in different colors so you can just see me doing it. I'm going to come in here from the left side in red. I'm coming in, I'm approaching the -5, and I know that when I get to it, I'm going to cross because, well, we determined that I have to cross. So I'm going to come up here and I'm going to cross through here like that. And then I've got to get back to 0. So I'm going to have to put a little arch on this thing. But when I get to 0, I'm going to bounce, right? And then I have to move into 1 and bounce off 1. So it's going to go like this. It's going to bounce off. Oh, shit. Oops. My hand slipped. Okay, so let me try that again. Go here. I bounced off. And then I bounce off again. And then I come up and connect. How does that look? Does it make sense how I put that picture together?
Yes.
Okay, good. Okay. Shall we do one more? Let's do one more. Okay, so how about this? Give me a moment here. I want to do something special. Okay, y'all ready for this? Yeah. X to the 5th minus 7x to the 4th minus 9x cubed plus 63x squared. Okay, so now before we do this, I just want you to just take a step back and think about this for a moment. If I would have started class today and I would have said, hey, everyone, let's draw that, right? Let's sketch that. You would probably be like what? Like, how in the hell are we ever going to sketch anything like this, right? It looks so complicated. It's not a quadratic, right? So you can't use the steps from quadratic. You probably look at that and throw up, right? It just looks so bad. But it is a polynomial function. And we should be able to do it. But this is different than any problem I've already given you. What, can someone tell me the big difference between this and what I've shown you already? There's a huge difference.
Not factored.
It's not factored. It's not factored, which means we will have to factor it. At some point, we will have to factor it. All right, well, let's not freak out yet. Let's just go through the steps. So the first step is to make sure it's polynomial, which I hope everyone would agree it is. The second step is to use the leading coefficient test to determine the left and right-hand behavior. But look, isn't this really good news? I mean, can't we just look at it right now and see what the highest power of x is? Because it's not factored, we don't have to look at like each piece and see like, what is this one acting like? What is this one acting like? If we just look at this, the highest power of x we see is 5, and the number in front is 1. There's no work to be done. So the degree here is 5, and that's odd. And the leading coefficient is 1, and that's positive. And so we know the left side goes down and right side goes up, because if we look at our table, odd degree and leading coefficient being positive was down, then up. The previous problem was just like that too, right? So you see how that step was just really clean because it was not factored? It's the third step that's going to suck, okay? We have to find the x-intercepts. And to do that, unfortunately, we have to take the function and set it equal to 0. And you see, we can't do what we've been doing. You can't. It's not factored. So you can't just set each of those equal to 0. We actually have to do that ourselves. We have to factor it. Now don't freak out, okay? What's the first step of factoring? First step always.
LCD.
GCF. I think that's what you meant.
Yeah.
GCF is always the first thing. Greatest common factor. So do all of these terms have something in common? They're common, right? But how about x's? Yeah, they all have at least 2 x's. So I can factor out an x squared, which would leave me with this. Right? Is everyone okay with that step?
Yes.
Okay, now we have to continue factoring. So look here at what's in parentheses. We've already done the GCF. So after you do GCF, the next step for factoring is to count your terms. How many terms do you have there in yellow?
4.
4, okay, so when we see 4, we try grouping, don't we? So that means we put a slash right behind the second one. And then we try and do a little bit of like GCF on the front and back. So let me do that. The x squared is going to stay here. Got a big set of parentheses equals 0. Now on the first two here, what do those two have in common that I can pull out? Don't they both have an x squared?
Yeah, x squared.
Yeah. Okay, so I can pull an x squared out, and if I do that, just from the first 2 terms, I should be left with an x minus 7. Now, if you remember how grouping works, we can say to ourselves, okay, well, what we need is on the second 2 terms, these 2 in black here, I need to be able to pull something out that would leave me with an x minus 7. So I need an x minus 7 in here. So what would have to come out in front here to make this work?
9.
9. Close, almost.
-9.
-9. -9. Because you have to have it distribute through to give you -9x and plus 63. And these 2 things match, right? Which is what you need for grouping. So my next line is x squared. Okay, now in here, because the x minus 7's match, I write x minus 7. And then I write the 2 things in front. Is that okay, everyone?
Yes.
Okay, there's one more thing. Let's see who sees it. Who's going to get the gold star for the day? It's one more thing I can do.
X squared.
Mm-hmm. What do you mean?
You do I think the x minus 9 and x plus 9.
Okay, yeah, so this right here, x squared minus 9 is a difference of squares. You have to recognize that it is. So that means that we could leave the x squared as x squared, the x minus 7 is x minus 7, but the x squared minus 9 can actually turn into x, not plus 9, but plus 3 and minus 3, and then equals 0. And there we go. We have factored it. Oops, sorry about that. So once we factor it, then we set each factor equal to 0. So here we set x to 0, then x minus 7 equal to 0, then x plus 3 equal to 0, then x minus 3 equal to 0. And so we get our answers: 0, positive 7, negative 3, and positive 3. What do I still need to determine? I'll give you a hint. What I put in blue there.
Multiplicity.
Multiplicities, right? So I need to figure out if I'm going to bounce or cross at each of these. So what's going to happen at 0? Am I going to bounce or cross at 0?
Bounce.
Bounce, because it's a 2. It's a power of 2 up there. I'm going to put a B for bounce. What am I going to do at 7?
Cross.
Cross, because it's a 1 up there. What am I going to do at -3?
Cross.
Cross, and at +3?
Cross.
Cross again. And once you have all that, you're ready to rock and roll here. Put all the X-intercepts. So I'm going to start at 0, put a dot here. At 7, I'll put a dot. At -3, I'll put a dot. And at +3, I'll put a dot. Next, I'm going to put the end behavior, which was left side down, right side up. And now I get to connect the dots. And I only bounce at one place. I only bounce at 0. Everywhere else I cross. So as I draw this, I'm going to cross through. Here's the 0. I'm going to bounce, then I'm going to cross, and then I'm going to cross, and then I'm going to connect it, and I'm done. So on your test, I'm going to give you a couple of problems where it's already factored.
You cut out again.
I did. So I will give you where it's already factored, and then I'll give you one where it's not like this. And so you'll have to do this procedure. Here's what we do.
It's cutting out pretty.
Is it bad? Yeah, I don't know why it keeps doing that. Let's take a break. Oh, 35. Okay, everyone. I thought I'd first show you this is actual just data of it's actually heart rate data from a bike ride that I did, I think yesterday. Anyway, just wanted to point out that even though it's jagged, it's roughly a polynomial. You know, polynomial functions go up and down and up and down and oscillate. They have different peaks and different valleys, and we see them all over the place. This is heart rate data, but you could look at stock market, anything, any data from a company showing, you know, money coming in or expenses going out. Usually we're going to have up and down. And so we need functions in math that can model those things. And that's why the study of polynomials is so important. We know parabolas, you know, they're important also, but you know, it's just a basic U shape. And if you want something more complicated, then you have to have a function that'll take care of that. And so polynomials are found throughout different applied sciences. And so that's why we study them here. So we have a basic idea of how we can get a visual picture of what they are. Okay, so y'all ready to try a few? I'm gonna give y'all 3 problems. Can y'all hear me okay?
Yes.
Yeah.
All right, so I'm gonna give you some problems. I'm gonna put y'all in little breakout rooms, and I'm gonna give y'all about 20 minutes to see how y'all do with these. So see if you can sketch these. Go ahead and write them down, because when I put you in breakout rooms, you're not gonna be able to see this. You know what? I want to change this last one just a little bit. Sorry. Okay, so see if y'all can do these. I'm going to put you on breakout rooms now. And there you go. You should get an invitation to go into a breakout room. There'll be 4 of you in each room. Just send me a message or something if y'all need help. But see if y'all can't help each other get through these. So we're looking for a sketch for each of those.